Section: Introduction. Let's dive into the world of meta-learning algorithms for image classification. These algorithms are designed to categorize a group of unlabeled images using only a few labeled examples. We refer to these labeled examples as the support set and the unknown images as the query set. In a scenario where we have n different classes, each with k labeled images, a situation we call an n-way k-shot meta-learning paradigm, the algorithm predicts the class of each unlabeled image in the query set from the n classes in the support set. Most meta-learning algorithms follow a three-step process: pre-training, meta-training, and fine-tuning. Pre-training involves setting up the meta-learner's feature extractor with a pre-trained vision model. Meta-training involves training the model's parameters to learn how to classify new visual concepts during inference by training the model on a series of n-way, k-shot classification tasks. Fine-tuning involves updating the model's parameters on the support set at inference. While meta-training is great at learning new classes during inference that are similar to those seen during meta-training, it often struggles to generalize to new classification paradigms. For instance, models meta-trained on coarse-grained object detection often fail to generalize to fine-grained image classification. Fine-tuning on the support set during inference can help improve a model's performance, but training a model during inference is often impractical and not suitable for many real-time applications. In this context, visual meta-learning algorithms are lagging behind recent advancements in natural language, where large language models, LLMs, show an impressive ability to learn new concepts during inference without fine-tuning. In our work, we develop a meta-learning algorithm that mimics LLMs by learning new visual concepts during inference without fine-tuning. We draw inspiration from in-context learning in LLMs and reformulate n-way k-shot image classification as sequence modeling over the support set and an unknown query image. To our knowledge, this is the first approach that enables in-context learning in the visual domain. Our approach first encodes support and query images with a frozen clip model and represents support set labels with an equal length and maximally equiangular set, ELMs, encoding. It then combines image embeddings with label embeddings to create a joint image label embedding and collates each embedded vector from the query and support set into a sequence. We then pre-train a sequence model, specifically a transformer encoder, across several large datasets with an explicit in-context learning objective. Classify the query given an input sequence composed of the support set and query point. This learning paradigm trains the transformer encoder to extrapolate to new classes in the parameter space of the model, enabling our approach to learn new visual concepts during inference without fine-tuning. We call our approach context-aware meta-learning, CAML. Our main contribution is to develop a meta-learning algorithm for universal meta-learning, the ability to learn any new visual concept during inference without fine-tuning or meta-training on related images. This challenging setting emulates the deployment of LLMs to real-time applications, and strong performance in this setting would unlock new applications of visual meta-learning. Our theoretical analysis shows that an ELMES is the encoding that minimizes the entropy of detecting classes within the support set, and therefore, does not need to be learned. Our empirical analysis highlights the importance of reformulating meta-learning as sequence modeling. Considering the support set and query together enables the model to attend to specific visual features of images in the support set to classify the query. Finally, our empirical analysis indicates CAML is a state-of-the-art meta-learning algorithm. On a diverse set of 8 out of 11 meta-learning benchmarks, and without meta-training or fine-tuning, CAML outperforms or matches the performance of P greater than M greater than F, a state-of-the-art meta-learning algorithm that is meta-trained on each benchmark. Now, let's talk about related work. Many recent meta-learning algorithms can be categorized as either gradient-based or metric-based. However, CAML belongs to a new category of context-based methods that casts meta-learning as learning over a sequence composed of the query and support set to predict the label of the query. Unlike other context-based methods, CAML avoids meta-training and can generalize to out-of-distribution classes during inference. Gradient-based algorithms learn representations during meta-training that can be quickly adapted to new data distributions by fine-tuning on the support set. Unlike context-based algorithms, they require fine-tuning during inference, which makes them unsuitable for real-time applications. Metric-based algorithms learn a distance-sensitive embedding space during meta-training, and during inference, the query is classified by its distance to points in the support set. While metric-based algorithms do not require fine-tuning during inference, they often perform poorly when encountering classes during inference that are significantly different from those seen during meta-training. Cross-domain meta-learning refers to a challenging evaluation paradigm where the meta-training and inference time data distributions are significantly different. Recent work finds that leveraging self-supervised pre-training, or foundational model feature extractors, can significantly improve cross-domain performance. Moreover, fine-tuning with respect to the support set almost always outperforms meta-learning without fine-tuning in this setting. While effective, fine-tuning is prohibitive to deploying visual meta-learning models in a manner similar to LLMs like ChatGPT, as the latency and memory cost to fine-tune a model's parameters on each user query is untenable. Moreover, fine-tuning is sensitive to the choice of learning rate, making these models difficult to deploy in practice. Section Summary. Meta-learning algorithms for image classification aim to classify unlabeled images using only a few labeled examples. These algorithms typically follow a pattern of pre-training, meta-training, and fine-tuning, but they often struggle to generalize to new classification paradigms. In this paper, we propose a meta-learning algorithm called Context-Aware Meta-Learning, CAML, that learns new visual concepts during inference without fine-tuning, emulating the capabilities of large language models, LLMs, in natural language processing. Our empirical analysis shows that CAML outperforms state-of-the-art meta-learning algorithms on multiple benchmarks without the need for meta-training or fine-tuning. Section: Approach. Our approach is inspired by the principles of in-context learning in language learning models, LLMs. We apply these principles to image classification, similar to recent work done in few-shot molecular property prediction. However, our work differs in that we avoid meta-training and instead focus on universal image classification. This means we aim to learn how to identify new visual classes during inference without relying on meta-training on related classes or fine-tuning on the support set. Our model, which we call CAML, is made up of three parts: a frozen clip image encoder, a fixed ELMS class encoder, and a transformer encoder sequence model. The clip image encoder is used to encode the query and support set images. The clip embedding space simplifies images into low-dimensional representations, allowing images with similar visual characteristics and semantic meanings to have similar embeddings. The ELMS class encoder is used to encode the classes of the support set. We have proven that an ELMS encoding of mutually exclusive labels allows the transformer encoder sequence model to best identify classes within the support set. The core idea behind CAML is to treat meta-learning as sequence modeling over the support set and query points. We use a transformer encoder as the sequence model and train it to predict the class of the query from an input sequence composed of the support set and query embedded vectors. We pre-train CAML's transformer encoder on few-shot image classification tasks from ImageNet-1K, Fungi, MSCOCO, and WikiArt. These datasets were chosen because they cover a wide range of image classification tasks. During pre-training, we only update the transformer encoder and keep the clip feature extractor and the label encoder frozen. In the theoretical analysis section, we explore the symmetries inherent in CAML. These symmetries allow us to formulate the problem of learning support set class representations as an entropy minimization problem with a closed-form solution. We prove that this solution is an ELMS. We also show that it maintains permutation invariance, a crucial property of meta-learning algorithms that ensures consistent predictions regardless of the ordering of elements within the sequence. An equal length and maximally equiangular set, ELMS, is a set of non-zero vectors that are all of equal length and maximally equiangular. This set of vectors has connections to both equiangular tight frames in representation theory, as well as the simplex equiangular tight frames highlighted in recent neural collapse works exploring softmax layer geometry at the terminal phase of training. Symmetry in the assignment of support classes to numeric labels is an important property of meta-learning algorithms. For example, if we have the support set classes, tower, bear, and tree, the mapping of bear to 1, tower to 2, and tree to 3 should produce the same prediction for a query point as a different mapping, bear to 2, tower to 3, and tree to 1. We postulate that the ability to distinguish among the classes of demonstration vectors is necessary for the model to predict the class of the query vector. Conversely, If a meta-learning algorithm predicts among D classes, and all classes maintain the same embedding, the model will be unable to identify the class of the query vector as all demonstration vectors appear to have the same class identity. We assume that the ability to learn a detector that maximally detects a given class will be beneficial to minimizing the loss for meta-learning paradigms. As we use the softmax of the inner product to determine class probabilities, maximizing the probability of a class is equivalent to minimizing the probability of all other classes. By symmetry in the assignment of class embeddings to support classes, we can assume that the number of detectors learned to detect class I is similar to the number of detectors learned to detect class J for all pairs I, J. Then the probability of a detector detecting class I for all 1 less than equals I less than equals D is jointly maximized if and only if the D class embeddings is an ELMS. When viewed through the lens of information theory, we can reinterpret an ELMS as the class embedding that minimizes the entropy of a detector detecting class I. Informally, ELMS causes a detector to have the least uncertainty when detecting class I. Section Summary. We propose a method called CAML for Universal Image Classification, which leverages the ideas of in-context learning to classify images without the need for meta-training or fine-tuning. CAML consists of a frozen clip image encoder, a fixed ELMS class encoder, and a transformer encoder sequence model. By pre-training the transformer encoder on various few-shot image classification tasks, CAML can detect new visual classes during inference. Additionally, we explore the symmetries inherent in CAML, such as the equal length and maximally equiangular set, ELMS, of vectors, which minimizes the entropy of detecting classes within the support set. Section. Permutation invariance. We want our model, CAML, to predict outcomes that are not influenced by the order of demonstrations in a sequence. This is known as permutation invariance. To prove that CAML has this property, we need to show that the ELMS label encoder, a part of CAML, is also permutation invariant. Let's imagine we have a sequence of labels, represented as a matrix S, and an ELMS label encoder represented by a matrix W. The label embedding, which is the result of multiplying S and W, doesn't change even if we rearrange the order of labels in the sequence. We tested our model on a variety of image classification tasks, divided into 4 categories: generic object recognition, fine-grained image classification, unnatural image classification, and interdomain image classification. The first 3 categories are standard benchmarks in meta-learning. We also created a new category, interdomain image classification, by combining natural and unnatural images. This allowed us to test how well meta-learning algorithms can generalize across different domains within the same class. For instance, the support image for the class tower might be Van Gogh's The Starry Night, while the query could be a picture of the Eiffel Tower. Humans can easily make this connection, but it's a challenge for meta-learning algorithms. We compared CAML with other models, including prototypical networks, MetaOpt, and MetaQDA, using the same pre-training and freezing their weights at inference time. We also compared it with the current best meta-learning algorithm, P greater than M greater than F, which is trained on each dataset. We found that fine-tuning, a common step in previous cross-domain approaches, is not compatible with universal meta-learning in real-time applications. Therefore, we didn't include it in our process. Our results showed that CAML outperformed other models in 15 out of 22 evaluation settings and matched or nearly matched the best-performing model in 5 out of the remaining 7 settings. Interestingly, CAML also performed competitively with P greater than M greater than F on 8 out of 11 benchmarks, even though P greater than M greater than F is trained on each dataset. This suggests that our approach of using foundational models and novel meta-learning techniques without fine-tuning can learn as much new visual information as directly training on in-domain data. However, P greater than M greater than F outperformed CAML on 3 datasets: CIFARFS, Aircraft, and ChestX. We believe this is because CAML and its pre-training process struggle with images that are downsampled or require fine-grained classification. For example, while a Boeing 737 and Airbus A380 have different labels in the aircraft dataset, the captions for those images may not be detailed enough to differentiate between them. This aligns with previous findings that CLIP, the model we used for pre-training, underperforms in specialized or complex tasks. Finally, we found that large-scale pre-training often decreases the performance of prototypical networks and meta-opt, likely due to overfitting. On the other hand, Camel and meta-QDA, which freeze the parameters of the feature extractor during pre-training, greatly benefit from this process. As visual feature extractors become more complex, fine-tuning or even loading these models into memory becomes less feasible. Therefore, models like Camel and meta-QDA, which don't fine-tune the feature extractor, will likely become even more effective. Section Summary. The section discusses the importance of permutation invariance in the output prediction of CAML, a meta-learning algorithm. It also describes the evaluation of CAML on various meta-learning benchmarks, where it outperforms other baselines in most cases. However, there are a few datasets where CAML is outperformed by P greater than M greater than F, possibly due to downsampling or the inability of the clip embedding space to differentiate fine-grained classes. The section concludes by highlighting the benefits of algorithms like Camel and meta-QDA that do not fine-tune the backbone feature extractor. Section. Despite its strong empirical performance, CAML presents several weaknesses. First, the maximum number of classes present in the support set at any point during inference must be known at pre-training to instantiate a B-group color, model green, $D$E group way elms. Further, at least one dataset during pre-training must use a B-group color, model green, $D$E group way classification setting so the B-group color, model green, $psi_I$E group class detectors referenced in sec. Theory are trained within the transformer encoder's attention layers. Another weakness relates to reliance on the frozen image encoder. As CAML does not update these parameters at all, it can underperform on tasks that are difficult to distinguish or highly spread out in the clip embedding space, such as low-resolution images or specialized fine-grained classes. Let's discuss some of the limitations of CAML, despite its impressive empirical results. Firstly, the maximum number of classes that can be present in the support set during inference must be known beforehand, during pre-training, to create a D-way elms. Additionally, at least one dataset during pre-training must use a D-way classification setting so that the psi_I class detectors, mentioned in the theory section, are trained within the transformer encoder's attention layers. Another limitation is CAML's dependence on the frozen image encoder. Since CAML doesn't update these parameters, it can struggle with tasks that are hard to distinguish or widely spread in the clip embedding space, like low-resolution images or specialized fine-grained classes. To better understand how CAML learns, we conducted empirical analyses on its ability to dynamically update its representations at inference time, and the impact of the fixed elms class embedding. Unlike other meta-learning algorithms, CAML, by recasting meta-learning as sequence modeling, considers the full context of a query and support set to predict the query's label. Specifically, the query dynamically influences the representation of support set points, and vice versa, as this sequence is passed through the layers of a transformer encoder. This property allows the model to update the support and query representations based on the task's context, not just the image's contents. An example of this is visualized in figure analysis sample tasks. Given only the 5 support examples, the prediction task is ambiguous. However, the nature of the query determines the prediction task. For instance, a query image of a tower reduces the task to generic object recognition, while a query image of embroidery reduces the prediction task to texture identification. We examined the representations of the support set and query vectors at the input to and output of the transformer encoder to analyze how dynamic representations affect CAML. For both examples, the transformer encoder learns to separate support set vectors by class identity and group the query representation with the correct support set example. We found that the frozen clip image embeddings are actually counterproductive for the classification by texture task. The query image embedding is closest to the support set example for the second class, oil painting. However, CAML, considering the full context of the query and support set, develops representations of the query in the context of the support set, and vice versa, to group the query with the embroidery support set image as they share the same texture, thereby correctly classifying this example. To supplement our theoretical analysis, we trained a version of CAML with learnable class embedding vectors instead of the fixed elms encoder. As expected, without any constraints or limitations, the class embeddings converge to an ELMS. The average pairwise angle between embedding vectors is approximately 1.77 plus or minus 0.02 radians, while the expected pairwise angle from an ELMES is 1.82. Similarly, the average norm of the learnable class embeddings converges to approximately 1.34 plus or minus 0.02, while the learned norm of the ELMS model is 1.32. We compared CAML with learnable class embeddings to the approach with a fixed ELMS encoder in the appendix. The performance is roughly the same on each benchmark, except for aircraft. In this case, the learnable embedding model significantly outperforms the ELMS model, and even surpasses all other universal meta-learning baselines on the 5-way one-shot split with an accuracy of approximately 66.3 plus or minus 0.2. However, given the similarity between both approaches on the remaining 10 datasets, and the learnable class embeddings actually forming an ELMES, we attribute the difference in aircraft performance to randomness in training the model, suggesting that the fixed ELMS encoder is indeed optimal.